Okay, a famous story from the history of machine learning. Some researchers were trying to create a machine learning algorithm that would look at pictures of dogs or wolves and correctly classify the animal. This is a dog or this is a well, the researchers, the pictures of wolves they used were all taken on the snowy tundra. So the machine learning algorithm looked at these pictures and it said, oh, when there's snow on the ground, the animal is a wolf. Obviously, we don't want stuff like that. So it's very important that we have a way of evaluating our machine learning algorithm and making sure that it hasn't learned nonsense. And that's where the concept of training and testing comes into play. And the idea is simple enough. We use one set of data to create the model, and then we test the model on another set of data. Now, ideally, these would be genuinely different data sets. But usually in big data, I mean, the data you have is the data you have. So rather than two genuinely different data sets, we just take the data that we have and we break it up. And we use maybe 80% of the data to train the model, and then the remaining 20% of the data to test the model. And again, this is not ideal because if the data set is flawed or the data set is biased, then we're going to see the bias when we do the training, and then we'll see the bias when we do the testing. I mean, what I'm trying to say is if we have training data like this, the machine learning algorithm can learn that snow means wolves. And then if we test it on data where all of the pictures of wolves have snow, the result of the testing will be that the model worked great when it obviously isn't. So that's unfortunate and it's something to be aware of. In Python or R or wherever, any situation where you might want to do machine learning, it's going to be easy to create a training data set and a testing data set, just because this is completely standard. And before I show you that, an important definition. What we're seeing with these wolves is an example of what we call overfitting. And overfitting happens when the machine learning algorithm comes up with a rule that is true for the data it's trained on, but not true in general. So the goal of training and testing data is to try to detect overfitting. To our wine example and just look at what we're going to modify here. We're now importing regression evaluator. So regression evaluator lets us take a linear regression and check it with a data set, and it says whether the linear regression is good or not, which of course is exactly what we want to do. So this is all the same. Here we split the data into training data and testing data. We do this randomly, 80% training, 20% testing, and then a seed just for reproducibility. Now we do the linear regression, and the only difference here is that now we're doing the linear regression specifically on the training data rather than the entire data set. And we output the results of the model just like we did before. Now we evaluate it. So we have this model. Where did it go? Here it is. We have this model, and we are going to take this model and we're going to hit it with test DF, the testing data. And now we're going to do something very similar to what we did before. We've got the label column and we've got the prediction column, which again is, I mean, at least sort of similar looking to, sorry, I lost it, similar looking to this, except what we're actually doing, maybe I shouldn't have called them similar. What we're actually doing is we're saying, good heavens, I keep losing it. What we're actually doing is we're telling it, well, here's the real quality. Here's the quality we predict based on our model. Please compare these things. And we define these test statistics, the error and the R squared, and we print everything. I never know how helpful it is going through Python code verbally. You might need to just play with it a little on your own. But you see, we now have multiple measurements of fit. Here's our R squared on the training data. And then here's our R squared on the testing data. And here's the error on the training data. And here's the error on the testing data. And the trend we see here is the trend we're pretty much always going to see. Our machine learning model is optimized on the training data, so it will perform better on it. The error on the training data is less than the error on the testing data. The R squared on the training data is better than the R squared on the testing data. And you will have to then make a decision of whether the R squared and the error you get when you test your model out are acceptable or not. 0.25 is, I think it's okay. Again, I mean, if this were like a physics problem, I would not think it's okay. I think it's okay given the extremely subjective nature of wine quality. Being able to explain 26% of the variance seems pretty good to me.